let's see. Okay, we're going to continue our discussion of fields. It looks like most of the class is missing today, but let me get 2 people in quarantine and 1 person out of the country. I was supposed to get a seating chart, but it's not very helpful. So 1, 2, looks like I'm supposed to have 4 here. So we've got 2 guys missing. So we'll see how the semester goes. I don't have the homework assignment up for today. It's almost up. There weren't problems from the text, but I've got 2 supplemental problems. So look for the homework today, and they'll have an S prefix in front of the problem number. That means they're in the supplemental. So we'll finish up chapter 2. We're discussing really just kind of fields in general, some preliminary discussion of electric and magnetic fields. I put up some equations last time, electric fields. We will get into much more depth on where those equations come from when we get into chapter 5, for example, on the electric field. Chapter 5 is devoted to the electric field. There's also a chapter 4, that reviews vector arithmetic or vector mathematics and things like, the dot product, the cross product, which we'll see today, which I think you probably saw in Calculus 3. You probably saw them in statics if you've taken statics. Is that correct? You've seen the cross product and dot product before. So again, part of this is a review, but I know in particular some of the stuff, divergence and curl that you run into in Calc 3, you go through pretty quickly. We'll certainly go over those again. But we've looked at a preliminary discussion of the electric field. So we want to look at the magnetic field today. Again, just some preliminaries, some basic definitions, some units. I'll put a couple of equations up here that, again, we'll go into much more depth later on. It's just a preliminary look at some of these concepts. On Friday, we'll go into chapter 3, which is on transmission lines. Okay, so it's actually certainly related to electromagnetics. We run into 2 types of waves in electromagnetics. We run into what are called unguided waves, waves that are sent out from an antenna, for example. Those are unguided. And then we have guided waves, waves that propagate in conducting media. And so those are things like coaxial cable, which is designed to carry high frequency signals. You guys have seen coax and connecting up a TV, or you've seen the cable, coaxial cable. There's also things like microstrip lines, waveguides are also examples of transmission lines. So we'll look at the theory of transmission lines. But everyone, at some point in their life has played around with magnets, and you know that magnets also create this, invisible force field. That's the concept we use to explain this attraction or repulsion or really force at a distance. We talk about those force at a distance concepts in terms of field theory, gravity fields, electric fields, magnetic fields. How does this thing that's, there's no direct physical connection like a rope or a rod, so how does this thing actually, attract or repel something at some distance away? You can also create a magnetic field by running a current through a wire. And you can intensify the strength of the magnetic field by actually making a coil of wire or something like an inductor. So this scene would be here. We can make this is called an electromagnet. There's another term for it. Could have an electromagnet over here on the right as well. So one electromagnet can, exert a force on another electromagnet. So, but we talk about, how this works in terms of field theory. We're going back to first discuss in terms of the force that's exerted. Okay. So a charged particle, we'll get to these concepts later on, attraction between two objects that create fields, but a charged particle in a magnetic field. So the magnetic field might be created by a magnet, might be created by an electromagnet, but we've got a charged particle in that field, feels a force only when the particle is moving. Okay, so I can draw field lines here. So generally use the magnetic field as a vector field. So we use the uppercase letter B to represent the magnetic field. It's actually more formally the magnetic flux density, just like we had the D field was the electric flux density. The B field is it's often just called the magnetic field, but more properly it's the magnetic flux density. And then the velocity of the particle is another vector V. So I'm going to show a particle here, and then say it's moving upwards. And our B field here is pointed to the right. Now again, this is different than our electric field. A particle in our electric field would actually feel an attraction or repulsion depending on the direction of the field, depending on the sign of the particle, sitting still. That's not true for the magnetic field. The particle actually has to be moving through the field in order to feel a force exerted on it by the magnetic field. If it's just sitting there, there is no magnetic force on the particle. The force on the particle it's a function of the amount of charge Q. It's a function of the velocity of the particle. And it's also a function of the field strength. The X here represents the cross product. And the magnitude of the field would just be Q times the magnitude of V times B. Well, and then actually because of the cross product, the sine of the angle between it. Okay. Let's see how much you guys remember about the cross product. If you've got two vectors, their cross product is a maximum when the angle between them is what? Do you remember? 90 degrees, yeah. The dot product is maximum when the two vectors are parallel. The cross product is maximum when the two vectors are at 90 degrees. Do you remember what the cross product is for two parallel vectors? It's 0. Again, we'll look at, there's a whole chapter devoted to this on at least vector mathematics. But the cross product here is actually, the result is, the magnitude of the result is would be the magnitude of V times the magnitude of B times the sine of the angle between them. Okay. Now in this picture, I've drawn B going due east, V going due north. Okay. So there's a 90-degree angle between them. So if V were actually direct, if the particle were moving due east, again there would be no force exerted on the particle by the magnetic field. Okay. It's got to be not only moving, we've got to have V, but we'll have, it also has to be moving at an angle relative to the magnetic field. If it's moving in the same direction as the magnetic field, there's no force. Okay. So another question about the cross product. Did you talk about the right-hand rule for determining the direction of the cross product? Okay, so you see it often maybe just done in two different directions. The right-hand rule I use is you put your index finger in the direction of the first vector. Okay. Your middle finger goes in the direction of the second vector. Your thumb then will be pointing in the direction of the cross product. Okay. The cross product always lies in a plane that's perpendicular to the two vectors. The two vectors define a plane. The cross product is always perpendicular to that plane. So in this picture, what would be the direction of the force? So index finger in V, middle finger in B, what's the direction of your thumb? Into the board, okay. I've drawn V and B on a plane, the plane of the whiteboard. So there's two possible directions for the perpendicular, either out of the board or into the board, right? The right-hand rule gives you that direction. In this case, it is into the board. And we'll talk more about that later. But right now, B is the magnetic flux density with units of Tesla, after the same Tesla that the cars are named after, Nikola Tesla, with units of Tesla, or equivalently Webers per meter. And I'm pretty sure that's not the same Weber that the grills are named after. But so, and those are actually equivalent units. 1 Tesla is equal to 1 Weber per meter squared. I think I said meter, but Weber per meter squared. So, you know, with a magnet, I think you guys have probably played around with iron filings, but in a magnet, the magnetic field lines are directed from the north pole of the magnet to the south pole. There is a fundamental difference between magnetic field lines and electric field lines. Magnetic field lines always form a closed loop. If you remember, for when I drew the electric field lines for a positive particle, the electric field lines were directed radially outward from that particle. But magnetic field lines always form a loop. I'm going to try and draw a coil here. I'm going to draw the direction of the field actually depends on both the direction of the current and how the coil is wound. Okay, if it's wound around to form, either in clockwise or counterclockwise. So I'm going to try and show, here these are the front sides of the coil. I'm trying to be pretty specific here in my picture. I'm not sure that pictures in the book are certainly a lot better. So if this marker were, a cylinder, this particular case, the coil is coming from the left side of my marker and then going into the board on the right side. That's how I'm trying to draw this coil, as opposed to coming out from the right side and going into the left side of the marker. So in this case, with the current in this direction, let me get this right. That direction field would be up. The field would be in this direction. I haven't put arrows on it yet. The north would be at the top, and the south would be at the bottom. And we'll get into, there's a rule for, right-hand rule for determining that field direction, but we'll get into that a little later. Okay. So it doesn't really matter if your figure's a little off at this point. If I reverse the current, the field would point in the opposite direction. Okay. With the current in the same direction, if I reverse the windings of the coil, the field would be in the opposite direction. If I reverse both the current and the windings of the coil, well, what direction would the field be in? The same direction. There is a material property that affects the magnetic field strength called permeability. What was the material property that affected the electric field strength? Permittivity. Okay. Permeability is also a material property. So I'm going to give you another equation so we can introduce this concept of permeability. A charge moving with velocity v creates a magnetic field Okay, now this is a different situation than the picture I drew here. Here I had a charge moving through an existing field, but a moving charge also creates a magnetic field. And we'll get into this later, but it creates this magnetic flux density field, this B field, which is a function of position, R. And then R is this vector that goes from wherever my charge is located out to my field point. My charge is at the origin of my coordinate system. And the corresponding equation is mu, the permeability, and then the field strength depends on both the size of the charge, the velocity of the charge. It's also an inverse square law. That means that the field strength decreases the farther I get away from the particle, the moving particle, with this 1 over r squared. And then the direction is given by a cross product again. It's perpendicular to both the velocity And this unit r hat is this unit vector that goes from my moving charge. So let's say I've got a moving charge. I'm going to put a coordinate system on here. So I'll call this the x-axis. And this is the y-axis. And then this is the z-axis. Okay. Of course, this charge might be moving in any direction relative to my coordinate system. So that's the velocity v of this particle. And then I pick a point, which is the point at which I'm going to measure the field due to this moving particle. The vector from that position vector from my charged particle to my field point, where I'm determining the field strength, is, I'm calling that little r. Little r is capital R times r hat. Okay. So r is the distance, capital R, the scalar is the distance between my particle and my field point, 2 meters, 3 meters, whatever. R hat is a unit vector in the same direction as r. There's a lot of stuff going on in this picture, right? Got a velocity vector, I've got a position vector. Now, again, two vectors will always define a plane. Let's assume I've drawn both v and r so that they're in the plane of the board. So v lies in the plane of the board, r lies in the plane of the board. Again, that cross product, v cross r, then the B field would be directed into the board at the field point. The direction is determined by V cross R, cross R hat, and would be directed into the board if both V and R were in the plane of the board. Let's say V were directed along the negative y-axis, and my position point was on the z-axis. What would be the direction of the field at my position point? So let's say V is in negative y, and I'm measuring the field on my z-axis. What would that be? Can you twist your hand around? V in the negative y, R is up, okay. So V is in negative y, R is up. Which direction is my thumb pointing in? So V out of the board, my middle finger up. So this thumb would be along parallel to the board. It's going to be in the negative x direction. Y cross z. Did I have that right? No, I'm sorry. It's negative y cross z is negative x. A little helpful reminder for cross products. If you arrange them in alphabetical order in a circle like that, if you move clockwise around the circle, x cross y is positive z. Y cross z is positive x. Z cross x is positive y. Okay. You go from the first to the second, you get the third is the result. If you're moving clockwise, it's a positive result. If you move counterclockwise, you get a negative result. X cross z is y. Y cross x, x cross z is minus y. Y cross x is minus z. Here, the problem I was talking about, V was in the minus y, R was in the z. Okay. Minus y cross z, that's this direction. Y cross z would give us positive x, but minus y cross z would give us the negative x. So, again, we'll talk a bit more about that, but certainly B, the intensity of our magnetic field, our magnetic flux density, increases with the amount of charge. It increases with the speed, the magnitude of the velocity. That's here in the numerator. This is a unit vector, okay, but the corresponding vector R has magnitude R. It decreases with R squared. So the farther away our point is, the weaker the field is. Makes sense. But it also depends on mu, and this is a material property that's called the permeability. Now, in free space, and air has about the same permeability as free space, we'll work a lot of our problems with in free space. The permeability of free space is 4 times pi times 10 to the minus 7th. This has units of henries per meter. It's related to inductance. If you remember, our permittivity was in farads per meter. Permeability is in henries per meter. Now, just like we work with relative permittivity, what you often find tabulated, and this is in Appendix A2 of your book. A1 was permittivities. Appendix A2 gives us several material permeabilities. Relative permeability μr is mu divided by mu0. And this is what you often find tabulated. In electric and magnetic field calculations, we need mu. Okay. But what you find tabulated typically is μr. How much stronger the permeability is above free space permeability. So to get mu, from our table, we get μr, multiply that by mu0. So because the magnetic field strength is directly proportional to mu r tells us how much stronger the field would be in a certain material over what it is in free space. Okay. So for the electric field, we had 2 fields. The E field, and what was the other one? What was the other symbol we used? The D field, the E and the D field. E was electric field intensity. The D field was electric flux density. Similarly for the magnetic, and when we work with magnetic fields, there's 2 fields. There's the B field, which is the magnetic flux density. There's also what's called the H field, which is the magnetic field intensity. And it's B divided by mu. It actually has units of amps per meter. Magnetic field intensity. And again, they only differ, at least for us, they only differ by this proportionality constant. Okay. So again, do we really need both? Can we work with one or just the other? For the problems that we're going to work with primarily, that's true. It's just that certain problems, in particular when you're working with boundaries between different materials, it's easier to work with the H field than it is the B field. Okay, often we'll work directly with the B field, but certain problems it's easier to work with the H field. Just like in some problems it's more convenient to work with the D field instead of the E field. For the H field due to a moving charge, the B field divided by mu. So in this problem, the magnetic field intensity is independent of the material. The magnetic flux density, the B field, would then be strongly dependent on the permeability. But for this particular situation, the H field is independent of mu. Independent of mu. So there's actually now 3 material properties that we'll be working with over the course of the semester. One is the permittivity. It has units of farads per meter. You can find some relative permittivities listed in Appendix A1. We use the letter, and then epsilon 0 is the permittivity of free space. Mu is permeability, with units of henries per meter. And Henry is the unit of inductance. And some relative permeabilities are listed in Appendix A2. And then the third material property that we'll be working with is conductivity. Use the Greek letter sigma for conductivity. Epsilon, mu, sigma are the Greek letters. Sigma for conductivity. The units here are Siemens per meter. Conductivity is a material property. It's actually it's the reciprocal of the resistivity. It's not conductance. Conductance is measured in Siemens. The material property, it's Siemens per meter. Yeah.
So the HR here, the magnetic field intensity, the one independent from mu. This is the epsilon, so it's dependent on the permittivity, not the permeability.
It doesn't depend on the permittivity at all.
That's a Q, not an epsilon.
Oh, okay.
Sorry. This is Q.
Yeah.
Yep. Thank you.
Now,
Yep. Sorry, I didn't know what you were getting at. So there's no epsilon there. And then the conductivity will work with, it relates, it actually relates the potential and the current. Okay, so there's a form of Ohm's law. It actually directly relates the electric field intensity and the current density. And so we'll see this later in the semester when we get to a relationship between the two. Okay. Let's work through an example problem that's similar to one of the homework problems. So I'm giving you 2 homework problems today. One is actually sketching some fields in 2 dimensions. The other one is a B field calculation. This marker just had it. Example. What is the B field at this is a point on the x-axis 2 meters out from the origin. So the position vector is directed from the origin. It's along the x-axis. Due to a 1 Coulomb charge with velocity v equal to 10 meters per second. It's directed along the z-axis. The velocity is up. Assume free space. So this position vector, this little r, it defines both the magnitude and the direction. So little r in our case is 2x. More generally, it has a magnitude and a direction. So in this case, since x is a unit vector, implies that r is equal to 2 meters, and that this r hat is just equal to x. So our B field is mu q v 4 pi r squared cross r hat, or 4 pi times 10 to the minus 7th, since we're operating in free space. This is mu 0. Q is 1. V is 10, and I'll pull, it's got a, it's directed along the z-axis. Oops, let me substitute in for r. And then in the denominator, I have 4 pi, and then I have the magnitude of r squared from that equation. So that's 2 squared. This quantity times z cross x, that's equal to this quantity multiplied by that cross product. So what is z cross x?
1.
It's what?
1.
Yeah, z cross x is y from the whole circle. Almost. No, yeah, no, it is. Z cross x is y. What's the magnitude of the B field? I think you're going to pull out your calculators for that. What'd you get?
Oh, no, I did it's 10 to the power negative 6 over 4.
Yeah, right, because the 4 pi's would cancel, 10 to the minus 6 over 4. So that's 0.25 times 10 to the minus 6. So I could say 0.25 microwebers per meter squared. So micro being the times 10 to the minus 6. Now, if this were in, the other common case, at least with inductors, instead of having an air core, is that the inductors wound around an iron bar. So the magnetic flux density inside the iron bar is going to be a lot greater than would be around an air core, because the permeability is much greater. So if this problem taking place and the surrounding material were iron with a with a relative permeability of 1,000, then the B field would be 1,000 times stronger. It'd be 0.25 milliwebers per meter squared in that case. Okay, that's it for today. We'll, actually, is everyone okay on, sketching some of these fields? Have you looked at those problems yet? Okay, we got a second. Let's just do two simple examples. X plus Y. Okay. Constant coefficients in both cases. So the E field here, the magnitude of the E field is the square root of the sum of the squares of the coordinates, but the coordinates here are 1 and 1. So this has a constant magnitude everywhere. And I'm just asking you to draw this in the XY plane. It's just too hard to draw in three dimensions. So X, Y. But it has the same magnitude. It's directed 1 unit along the x-axis, 1 unit along the y-axis. So it'd be like that. Everywhere it's like this. Okay. So all my arrows here are supposed to be going in the same direction. I'm not sure I'm succeeding with that. And then everywhere, in this particular case, no matter where I am on the XY plane, or actually in the Z plane in this case, there is no Z dependence in this field. The E field would be directed, at an angle 45 degrees above my x-axis, okay, and have the same length everywhere. Okay, the length is kind of a relative thing here. I showed it as square root of 2. That would actually be, for a length of a box, for a 1-1 box, it would be kind of the diagonal there would be the. When things get a little harder is when the magnetic field strength varies as a function of position, like it does here. Now the magnetic field strength here would actually just be equal to X. And it's always y-directed. It's always pointed up. That's what the unit vector is. So this field is always pointed up, but the length of my vector varies depending on my x position. When x is 0, what is my electric field strength? 0. Okay. So that's right here, right? There is, 0 pointed up is the same as 0 in any direction. But at 1, okay, it's pointed up, it has a length of 1, x equal 1. At 2, pointed up, but it would be twice the strength at 1. At 3, it would be 3 times the strength. Okay. Now this electric field, though, exists at all points in space. Okay. So, here what I would do is represent the smaller field strength with smaller arrows. Everywhere on this line, though, the electric field. And so we represent the greater field strength here with the longer lines. Now, again, this is everywhere. At 0, it's here. Now, when x is -1, the field is going to have, you know, a length of 1, but now it's going to be in the minus y direction. Okay. So at -1, these arrows would be like this. And then at 2, it would be twice as long. And at 3 times as long as they are at 1. This particular case, this field gets stronger the farther we get away from the vertical y-axis, right? And so that field would look like that. So I'm giving you some of these problems to sketch these various fields. They're not easy. You'll have to think about them, I think, a little bit. Calculate the magnitude, say, well, what's the magnitude at this point? What's the direction at this point? But I think these exercises will pay off later on when we start having to work more with these fields and cross products and dot products and things like that. Okay. That's it for today.
You're going to put this in the notes I send you. This one.
Please, yeah.